Hello everyone, my name is Lee. I'm assistant professor at Ulsan National Institute of Science and Technology, UNIST, in South Korea. In this talk, I'm going to present our paper, Weight Separation for Memory Efficient and Accurate Deep Multitask Learning. Let me start by talking about the motivation of this work. As deep learning algorithms for resource-constrained devices continue to become more efficient and more accurate, we see an increased number of intelligent embedded systems, such as home IoT devices, social robots, and a plethora of portable, wearable, and mobile devices that are packed with a variety of machine learning tasks running on the same device. For example, home hubs like Amazon Echo Show and Google Nest Hub nowadays can perform voice recognition, face recognition, emotion recognition, and gesture recognition in order to closely intimate human assistants. Similar machine learning models are running on social, domestic, and personal robots, which also execute robotic application-specific learning tasks such as object detection, place classification, person identification, and scene understanding. There are some existing works that try to solve this problem, which enables multitask learning on a single device. The first approach is the DNA model compression, which compresses individual DNA models into smaller sizes so that their total memory size can be reduced. Although this is the most popular approach to employ deep neural networks on embedded systems, it is not scalable since only a limited number of DNNs can fit into the main memory even after compression. And also, it does not perform multitask learning that can bring collective performance improvement of multiple DNNs as they are independently trained, which does not increase the prediction accuracy of each DNN by exploiting the commonalities and differences across different tasks. And lastly, the compression method requires the modification of the well-established original network architecture, which might cause unexpected behavior at runtime. And also, many compression techniques require time-consuming human effort with high cost. Another approach is multitask learning. Given multiple DNNs, multitask learning generates a single unified DNN by jointly training all the DNNs together at the same time. Although the multitask learning approaches can achieve some memory saving by generating a single DNN model for all tasks instead of generating an individual model for each DNN task, it only works for DNNs having similar network architectures that perform similar tasks. And also, multitask learning approaches are not capable of coalescing many DNNs, as DNNs must share a macro or a larger structure. For example, first few layers of the network, and thus it can miss the opportunity to coalesce DNNs when there are similarities between DNNs at a micro-level structure. For example, weight parameters. Recently, a new weight parameter sharing method among multiple DNNs named neural weight virtualization has been proposed to enable in-memory multitask learning. So in this approach, all the DNNs are packed into the main memory, RAM, without using any secondary storage such as a flash disk or hard disk, which enables fast and scalable in-memory multitask learning. However, the major downside of this work is that prediction accuracy of the in-memory DNNs degrades quickly as more DNNs are added to the main memory. Also, since this approach only utilizes the main memory, RAM, DNN models whose size is larger than the main memory capacity cannot be deployed. In this paper, we solved the aforementioned problems of all the existing works, especially the previous neural wave virtualization method. Unlike the neural wave virtualization approach that only uses the main memory for multitask learning, we argue that by optimally using both the main memory and secondary memory storage, the possible loss of prediction accuracy can be effectively retained with the separated weight parameters. So in order to do that, we propose a weight separation approach that optimally distributes the weight parameters of multiple DNNs that participate in multitask learning between the main memory, RAM, and the secondary memory storage, such as flash disk, in order to achieve memory efficient and accurate model inference. To this end, we take an information theoretic approach to separate weight parameters into two types of weight parameters. The first type of weight parameters are inessential weight parameters that are assumed to contribute less to the prediction accuracy, which takes the majority of weight parameters. We call this type of weight parameters as shared weight parameters, which can be shared with each other DNN's weight parameters that saved in the main memory RAM in order to reduce the overall memory requirement. The second type of weight parameters are critical weight parameters that are assumed to play a significant role to provide an expected prediction target accuracy. We call these prediction accuracy preserving weight parameters as exclusive weight parameters, which we must preserve unaltered in order to ensure the desired prediction accuracy. They are exclusively saved in the secondary memory, such as SSD, without sharing. Those two types of weight parameters, shared weight parameters and exclusive weight parameters, are distributed between the main memory and the secondary memory in order to simultaneously achieve two seemingly incompatible objectives, that is, memory saving and prediction accuracy preservation. This figure illustrates the overall concept of weight separation, where the weight separation enables the multitask learning execution of multiple deep neural networks, DNNs, with the limited system memory, while providing the desired target prediction accuracy. The proposed weight separation identifies which weight parameters are inessential and which weight parameters are critical to prediction accuracy. The inessential and critical weight parameters are placed separately in the main memory and secondary memory of the system, respectively, so it can achieve low memory and accuracy preserving multitask learning on a memory-constrained embedded system. From now, I'm going to describe the procedure of the proposed weight separation. The first step of weight separation is to compose weight pages of DNN. The weight pages of DNN are formed by grouping each weight parameters with a fixed size of memory blocks. The generated weight pages are then called primitive weight pages that become the basic unit of weight separation, which means that we deal with weight parameters in the unit of primitive weight pages in this work. After the primitive weight page set is composed, the amount of contribution of an individual weight page to the prediction accuracy is estimated in order to separate the primitive weight pages into less important shareable weight pages and more critical exclusive weight pages. The contribution of weight page is measured by empirical Fisher information, EFI for short, as shown below. Here, F on the left-hand side is the empirical Fisher information of individual weight parameter theta. And F on the right-hand side is the output of DNN given input X. And then the contribution of an individual web page is measured by summing up all the empirical feature information of web parameters belonging to the same web page. Once the contribution of web pages are measured with empirical feature information, the connection between the prediction accuracy, loss value, and empirical feature information is identified in order to find the exclusive web pages that are required to ensure the target prediction accuracy. Here, first, we set a target prediction accuracy of a DNN, for example, 0.95 classification accuracy. And given this target prediction accuracy, we can convert it to the corresponding target loss value, for example, 0.4321. That is more convenient to analyze with EFI measurement of web pages. And then this target loss value can be converted into the empirical feature information. For example, 0.0715 in this example. So the reason we convert the target prediction accuracy to empirical feature information, EFI, is that we can identify how much each web pages contribute to the target prediction accuracy in terms of EFI. So in order to do that, we use the loss value as the bridge between them. Since we already have measured the EFI of each web parameters, of which total summation is equal to the EFI converted from the target prediction accuracy, it becomes also able to estimate the relative contribution of each web page to the target prediction accuracy indirectly. So here shows the detailed equation used for the conversion between them, which I will skip to explain in this talk. For more detailed mathematics, please refer to our paper. Given the loss value of original source DNN and the target loss value to achieve after weight separation, the relative performance ratio of the DNN with weight separation to the source DNN, which we call target performance rate, is defined in order to set a performance criteria. So here, the target performance rate is calculated by using the loss value of the original source DNN and the 2B weight separation DNN, which is 0.9663 in this example. And next, based on the relationship between the EFI of a web page and the loss value we have looked at the previous slide, the relative contribution ratio of a web page to the loss value, which we call contribution density, is derived as shown below. So the contribution density represents the relative extent of total loss change expected when the web page is changed, measured by the expected loss gradient of the web page. And then, given the parameter web page set and their contribution density and the target performance rate, the exclusive web page set is selected as the minimum subset of parameter web pages, which ensures that the target loss value is within the range of performance margin as follows. So here, PME is the minimum set of exclusive web pages we want to find. And here, the VM is the target performance rate, which is 0.9663 in this example. And this right-hand side summation is the total contribution density of web pages. In order to find the exclusive web pages, which is a variation of the subset sum problem, which is also an NP-complete problem. All the primitive web pages are first sorted in descending order by their contribution density. And then the top n web pages having the largest contribution density are selected as the exclusive web page set, such that difference between their total contribution density and the target performance rate becomes smaller than the performance margin. And then the remaining web pages not selected as exclusive web pages become to constitute the shareable web pages set. Putting it all together, this figure shows an example of weight separation. First, the weight parameters of DNN-A are grouped into 10 primitive weight pages, which is shown as gray color. And then, given the target prediction accuracy, for example 0.95, weight pages are separated into 8 shareable and 2 exclusive weight pages, which are shown as blue and green color, respectively, based on the target performance rate and contribution density of each weight page. And then, the shareable web pages of other DNNs are overlapped onto the shareable web pages of DNN-A. The shareable web pages of multiple DNNs are packed together into the limited size of main memory of the system via overlapping. We use the neural wave virtualization method when overlapping the shareable web pages. This figure illustrates two steps of overlapping the web pages onto the limited number of shared web pages on the main memory. The first step is web page overlapping, and the second step is shared web page optimization. As we can see, multiple shareable web pages are combined as a fewer number of shared web pages indicated as red boxes. So for more detail of the procedure of web page overlapping, please refer to the neural wave virtualization paper. The shared and exclusive web pages are separately distributed to two memory levels of the system, that is, main memory and secondary memory, respectively, which enables low memory multitask learning with target prediction accuracy. So this figure shows the web page memory distribution. The shareable web pages, blue color in the left and right of DNN-A and DNN-B, are overlapped with each other and combined to the shared web pages, blue color in the middle, that fit into the main memory. And exclusive web pages of DNN-A and DNN-B, yellow and green color in the figure, are placed in the secondary memory exclusively without being overlapped in order to ensure prediction accuracy. Each DNN has a web page table that translates the web pages, including both the shared and exclusive web pages, into the primitive web pages representing the necessary original web parameter of the DNN. This figure illustrates an example of web page table where 8 primitive web pages of DNN-A are translated from 6 shared and 2 exclusive web pages by the web page table. It enables an efficient representation of a massive volume of web parameters as the size of web page table decreases proportionally to the web page size. For evaluation, we implement an open source software framework of the proposed weight separation by extending the TensorFlow and CUDA library, which performs the weight separation and multitask DNA execution on GPUs. For the low-end microcontroller of the multitask IoT system, we separately implemented the C language version of it. Two hardware platforms are used to implement the multitask IoT system and mobile system. The multitask IoT system is the MSP430 microcontroller using 131 kilobyte of internal FRAM as main memory and 2 megabyte of flash disk as the secondary memory. And then for the multitask mobile systems, we used Jetson Nano embedded GPU system using 156 megabyte of GPU RAM as main memory and 2 gigabyte of eMMC as the secondary memory. The first experiment is to evaluate how much memory usage can be reduced by the proposed weight separation. This table shows the memory usage of the multitask IoT device where the weight parameters of 10 DNNs are separated into shared and exclusive weight pages. The result shows that the weight separation improves the memory efficiency by 5.9 times, where 1,245 kilobytes of shareable weight pages are distributed and packed into 131 kilobytes of FRAM, while 96 kilobytes of exclusive weight pages are distributed into the flash disk. It also shows that the only 9.5% of weight pages are required to be exclusive in order to provide comparable prediction accuracy, which will be shown in the next slide soon. Another experiment on memory efficiency is to compare the memory usage of weight separation against three alternative techniques, that is, neural wave virtualization, DNN compression, and multitask learning. The right figure shows their memory usage along with vanilla DNNs that do not apply any of these techniques. The weight separation achieves slightly larger memory usage than the smallest one, that is 227 kilobyte versus 144 kilobyte of neural virtualization, while achieving more than 2 times memory reduction when compared to the multitask learning. For embedded GPU-based multitask mobile system, weight separation achieves 4.7 times the memory saving, as it reduces the memory requirement of 10 DNNs from 1062 megabytes to 227 megabytes. It implies that although only 10 DNNs are learned together here for each system in this experiment, a more significant number of DNNs can also be learned with considerable memory reduction by having a relatively small portion of exclusive weight pages that slowly increases over the number of DNNs. The next evaluation is to compare the prediction accuracy of weight separation against three alternative techniques, that is, neural wave virtualization, DNN compression, and multitask learning. And this figure shows the prediction accuracy on a multitask IoT device along with vanilla DNNs that do not apply any of these techniques. The result shows that the weight separation achieves 11.6% higher prediction accuracy on average. It is assumed that three aspects of the proposed weight separation enable higher prediction accuracy than the three alternatives. The first is there is no modification of DNN architectures, and the second reason is that the proposed weight separation identifies and preserves critical weight parameters, and the third reason is that it performs joint optimization that enables better generalization and less overfitting. On the other hand, each alternative method exhibits different shortcomings that are presumed to cause lower prediction accuracy than weight separation approach. That is, the neural wave virtualization neither separates nor keeps important weights intact. And second, the DNN compression method deforms the model architectures. and multitask learnings have difficulty in creating a unified network of heterogeneous deep neural networks. For the embedded GPU task mobile system, we see the similar result. So here, the weight separation also achieves 6.3% higher prediction accuracy on average when compared to the all three alternative methods. The last experiment is to compare the end-to-end execution time of weight separation against the three alternative techniques. The below figure shows their execution time along with vanilla DNNs. The result shows that the weight separation achieves a little bit lower speedup when compared to the fastest ones, that is 1.6 times for multitask IoT system and 13.1 times for the multitask mobile system. Although the exclusive web pages that placed in the secondary memory are the main reason for the slowdown of acceleration, they ensure comparable prediction accuracy of DNNs, unlike the two faster alternatives that blindly accelerate the execution speed without considering target prediction accuracy. Thank you so much.